Greetings, math friends. I want to start out by doing a bit of a proof for the relationship between the cosine of theta to the sine of pi halves minus theta. The two functions cosine and sine are defined as a relationship between the angles of a right triangle and side ratios of the same right triangle. So I want to start out by talking about that. If we want to look at the cosine of theta, that is, it relates the adjacent side to the hypotenuse. And I'm going to label the change in this direction as x, the change in this direction as y, and the change in the diagonal direction here as r. If you envision this triangle in a circle with this vertex centered at the origin, then this is the radius of that circle, a lot of times portrayed as the unit circle, where the radius is 1. We have this angle will be related by this function to this ratio of sides. If we look at this other angle up here, by the triangle angle sum theorem, we see that these three angles have to equal 180 degrees. 90 degrees is taken up by the single angle here, so that means that theta plus alpha has to equal 90 degrees. That means that this is a pair of complementary angles. Some of you may or may not know that cosine actually is shorthand for the complement of sine, because there is a relationship between these two angles here. If we look at the sine of alpha, that relates this angle to the ratio of sides of the opposite side over the hypotenuse, which means that these angles are related to the same side ratios through two different functions, so that sine of alpha and the cosine of theta are equal to each other. That's not quite what we said we want, though, because we want the cosine and sine related to each other in some way with the angle theta. We're also going to make use of this. So I said 90 degrees here, which is how a lot of people define the right angle. But I said up here we want to be in radian measure. 90 degrees is equal to pi halves radians. So really what we're saying is that theta plus alpha is equal to pi halves when we're talking about radians. That we can make use of. Pi halves minus theta has to be alpha. If you subtract theta from both sides of this equation, you have 90 minus theta is alpha, and again, 90 degrees is pi halves. So we can make a substitution here with alpha that this is the same as saying the sine of pi halves, again, this 90 degrees if you're used to degrees, minus theta has to be alpha. So then we have this statement and this statement, which are equal to each other by the transitive property, and so we have verified this statement. Now that we have verified that cosine is really sine, as Jens Felau likes to say, if you're brave enough, everything is a sine function. We are going to look at these three problems when they're all converted into sine. I already have the Pythagorean identity here as all sine functions. Having converted all of these exercises into sine-only functions, we're now going to go ahead and solve these because we are brave enough. Looking at our first exercise, we are going to turn this product into one fraction. Sine theta times sine of pi halves minus theta, but this is secant. And then sine of pi halves minus theta all over sine. So that's this product rewritten as a single fraction. We see right away these cancel because you're dividing by sine in the numerator and denominator. And then these are inverses of each other, denoted by the -1. The reciprocals, actually. But multiplying them together, they give you the multiplicative identity. And that, of course, is the sine of pi halves in radian measure. So this is going to be our final answer here. Looking at our second problem, we're going to focus on this product first. And we see that this and this are going to cancel again. And that's going to leave me with the cosecant minus the sine. This, of course, is a fraction. And this we are going to put over 1 so that we can start to see the subtraction. We need to have common denominators. So we're going to multiply top and bottom by sine. Then we end up with 1 minus sine squared theta over sine theta. And we can do a Pythagorean substitution here. This is going to be sine squared of pi halves minus theta all over sine theta. And that is as far as we can go with that. And then lastly, looking at this product of cotangent times tangent, many of you probably know those are reciprocal functions. They multiply together to give you the multiplicative identity. Written as cotangent and tangent, that may not be as obvious to people unfamiliar with it, but when you bravely look at this as sine functions, you see that on the diagonal of this multiplication, we have the matching values. So this is going to cancel with this is going to cancel with this, and again, we are going to end up with the multiplicative identity of sine pi over 2. So actually number 3, while some of these others may lead to some confusion or a little more intense thinking, we actually see a simplification as we look at exercise 3. So this is going to be our final answer here. I hope this has been interesting. It's a bit amusing. The challenge is nice and really helping to understand the processes going on here. Hopefully you find some mathematics in the world that you can share with others and enjoy. Cheerful calculations.